While solving many physical problems, we often have to switch from one coordinate system to another. This is done in order to make it easier for us to solve the problem. The choice of the coordinate system is a very important factor which helps us in that direction. In the case of hydrogen atom, we have seen that the coordinate system chosen is the spherical polar coordinates instead of the Cartesian coordinate system. In this video, we will discuss why the choice of the spherical polar coordinates is natural in the case of the hydrogen atom. Why spherical polar coordinates? Let's answer this important question by considering one of the most significant problems in quantum physics, particle in a three-dimensional box problem. In this problem, your particle will be free to move within a box whose walls are defined by the potential, which is infinite at Lx, Ly, and Lz, which are the lengths of the box along the x, y, and z direction. The potential will be zero within the box, which helps the particle to move freely within the box. So the natural choice of the coordinate system would be the rectangular coordinate system, or in other words, your Cartesian coordinate system, because the shape of the box is has a resemblance to a rectangle, and the importance of selecting this coordinate system is that it enables us to write the wave function as a product of different functions. Each function will be dependent only on one coordinate system. So if you substitute this in your three-dimensional Schrodinger equation, then you will be able to reduce your three-dimensional Schrodinger equation into three one-dimensional Schrodinger equations, which will be much easier for you to solve. So after the solution, you will be getting your energy eigenfunctions like this, which will be a product of three sine functions along x, y, and z directions, and the total energy would be Ex, Ey, Ex plus Ey plus Ez, which will be the energy components along the x, y, and z direction. So the choice of rectangular coordinates here makes it easy for us to solve the problem. Rectangular coordinates are well suited to define the motion of a particle along a straight line as well as simple curves. But when we study much more complicated trajectories, problems arise. For example, the motion under the influence of a central potential. Examples of this motion include the motion under gravity and electromagnetic field. Here, the trajectories are much more complex to be handled easily with the Cartesian coordinates. Let us consider the case of hydrogen atom now. Its electron is free to move around the nucleus in various allowed paths. If there is a line connecting the electron and nucleus, and we assume that it has a fixed length, and then it is allowed to move in all directions around the nucleus, it will certainly trace a sphere around the nucleus. Thus, the spherical symmetry of the problem becomes immediately evident. This is like a particle in a spherical container, and we can still use Cartesian coordinate systems to solve this problem. But the potential, which is Coulombic in nature, has to be defined at each and every point on the sphere, and the solution will include a lot of sines and cosines, which will make it a lot complicated. This is because we have not chosen the natural coordinate system for the problem, which is the spherical polar coordinate system. A spherical polar coordinate system contains three coordinates: r, theta, and phi. Phi is actually the azimuth angle which is obtained by projecting r to the xy plane. Now, your theta can vary from 0 to 180, and your phi will vary from 0 to 2 pi along the xy plane. So in order to construct this sphere, you will have to fix your r value, and then you have to rotate it by 2 pi in the xy plane for a fixed theta value. By changing theta, you will get different circles, and their combinations will form a sphere like this. So if we use this kind of a coordinate system, that is a spherical polar coordinates in this problem, then we will be able to write the wave function for the problem very similar to the that in the case of particle in a three-dimensional box. Here you can see that psi is equal to r into theta into phi, and this r, theta and phi depends only on a single coordinate system. So the immediate effect is that you can split the three-dimensional Schrodinger equation into three one-dimensional Schrodinger equations, and the problem will be a lot easier to tackle now. So the main trick involved in the choice of coordinate system or its selection is to identify the symmetries involved in the problem. So in the case of a system for which there are three rotational symmetries, then it's wise for us to choose the spherical polar coordinates. On the other hand, if the system has a translational symmetry and also two rotational symmetries, then we better choose the cylindrical coordinate system. If there is only translational symmetry, we will go for the Cartesian coordinate system.